All right, I sent the link. I get to introduce us, so that'll be the best part. This first 3 seconds usually isn't even captured, which is great.
Watching an ad.
Good, ads are good. I'm interested in the audio too, so if you can listen to that.
I'll wait till the ad's done.
Hi everybody, if you can see me. What ad are we getting today? What type of thing is advertising?
This was a video game, I think.
Video game, okay.
Which one?
You're
I'm on? Okay. All right, can you crank up the audio so I hear myself? All right, welcome to our week 6 special live in-person lecture. We are on the Mount Pleasant campus in a computer lab. We're going to be using the whiteboard today, and the main subject today is colors. And the audio seems to be working. If you have any questions throughout the lecture today, please either type them in the Twitch chat, which is perfect as usual, but we're also monitoring the Slack channel. So if you have questions and you want to post them in Slack, that is cool too. I'm Brandon Kish. I am teaching web design this semester with a co-teacher. And our co-teacher is going to be giving the lecture today. That's Anthony Freds. Say hi.
How's it going?
Color is an important aspect of web design and art in general, and we're going to be taking you from some art theory through how color is implemented from a technical standpoint, all the way to how to use it in your HTML and CSS today. So without any further ado, here's Anthony.
Thanks. Thank you, Brandon. How's everybody doing? No snow today. That's good, right? We're going to get right into it. What I have here on the board, we're going to have 3 steps to this lecture. We're going to start here with primary colors. We're going to end up in the secret category here, and then we're going to end up here with hex FF, FFFF. And when we get there, hopefully we'll have a good connection between these 3 things to understand how this is going to affect your decision making in web design in terms of colors, and also in terms of the coding for colors. And then what I'd really like to get at is the why. And in terms of what you need to know for the course, I'll point out some of the things that you should know, but the rest of it is more to have an understanding. If you have any questions about this during the lecture, then make sure that you ask, and we'll address those immediately. There's going to be a lot of stuff in here that may be new to you, and there's also going to be some math. So we're going to, what I expect from you is that you have a general understanding of why the math's there, but I'm not going to ask you to recreate the math for the class. It's more just to have that contextual understanding. So we'll start with this. This brings us back to kindergarten, 1st grade. Primary colors. What are primary colors? I'm looking at the camera, but I'm asking you guys to. So we're listing them. That works. So we got blue, we got yellow, red. Okay. And why do we call these primary colors?
Because you can't mix any colors to make them.
Oh, okay. So we have a definition that these 3 colors, you can't mix any other colors to get these colors. So you have to actually have these colors in place. So in this case, we're talking about, let's use the example of paint. So if you wanted to mix 2 or more different colored paints, you would not be able to get these 3 colors. But what happens when you mix these 3 colors in terms of paint? What happens when you mix blue and yellow?
Green.
Green. And what about yellow and red?
Orange.
Orange. And then we've got blue and red.
Purple.
Does that look good? Is everybody in agreement that this is all true stuff?
Just with paint though, right? Like
Just with paint?
Computers can actually have a fourth color, it's magenta.
Okay.
I don't know any of
We'll
that.
put magenta over here for now. Okay. So if we mix, in terms of paint, if we mix these three colors, if we had a bucket of blue paint, bucket of yellow paint, bucket of red paint, and we mix them in even proportions to the colors, we're going to get these other three colors. But would you agree that we could mix these three paints in a way to get every other color? Or not? Out of paint?
Essentially, yes,
Essentially, yes.
because they all come from those three colors. So you would be mixing all of those colors just mixed with other colors with it, such as your orange mixing with your blue, or your orange mixing with your red.
Okay, so how would we get,
How'd you pink?
how would we get pink? What would you do?
Get white paint and mix it with red.
Okay, well, let's add that. Let's add these two, white and black, which are not primary colors. But in theory, if we mix these paints equally, which one of these colors would we get? Get black. Problem is, in reality, we're generally using pigmentation that's either chemically produced or found in nature. And when we mix those three colors together, we actually end up with kind of a muddy puke brown. That's how I would describe it. You're not going to find a Crayola crayon with the label puke brown, but you can imagine what it looks like. And so there's a tendency or not a tendency, but the way that we deal with that in terms of paints, inks, printer inks, we actually do not mix these. We just add black. Probably make more sense if I used a black marker. We just add black. Because when you mix those three together, it doesn't actually produce black in reality. So here's the problem. First of all, do we have 100% agreement that these are the primary colors for paint?
No one's disagreeing in the chat room.
No one's disagreeing?
No.
That doesn't necessarily mean agreement. But we'll go with that. Nobody's disagreeing. What if I told you that your kindergarten teacher, Mrs. Snidely, I'm assuming she was your kindergarten teacher. What if I told you that she wasn't telling you the truth? And you've gone your entire adult life thinking those were the primary colors.
Why would a teacher lie to you?
Well, I don't think they meant to lie. I think that they just didn't understand. Because if you go to your Crayola box, or you go to the paint store and you get blue, yellow, and red, and you mix them, you're going to get green, and you're going to get orange, you're going to get purple. But technically, and I'm coming back over here because someone had mentioned magenta. Technically, got cyan, yellow, magenta, which are usually put together as C, Y, and M. And these, to a young person, if you, of course, the yellows match up. So yellow is actually primary color. But blue and red are very, very close to cyan and magenta, where if you asked a young kid, someone in kindergarten, if you showed them paint that's cyan or printer ink that's cyan, they're not going to remember that. It's not these two words are not commonly used. We usually teach kids very simple color names that correspond with the crayons, and so these are more popular, but they're not accurate. What we're actually dealing with is cyan, yellow, and magenta. And then, as I mentioned, because when you mix these, then you don't actually get a black. Then we actually add a black ink cartridge to our printers. So you've likely seen these letters CYMK together. If you've used Photoshop, then that's something you might have seen. But these are the actual primary colors for paint. So let's take. We're gonna continue to use the kindergarten lexicon, though. We're gonna continue to think in blue, red, and yellow because we've done this our whole lives. So I got this box. This is where you say.
What's in
What's
the
in the
box?
box? Anything?
What's in the box? What's in the box? Funny you should ask that. Got a couple things in the box.
We have a guess. Who thinks it's pizza? Is there pizza in the box?
If there was pizza in the box, there would not be pizza in the box because I haven't eaten lunch yet. So it's not pizza, which means it could have been pizza. But instead, I've got this red pin, and we're gonna agree that this is red. So
You know, I want to make sure that everyone gets a good look at that. So we got two views here. Can you hold the pen up to this one? There we go. Everyone see the red pen? It's like a magic show, right? Everyone needs to
Yeah.
see there's nothing special about it.
nothing up my sleeve. Nothing up my magenta sleeve. Okay, so we got the pen. So can we, for the purposes of this experiment, we all need to accept that this is red. If anyone disagrees that this is red, we must stop now and find out and make sure that everybody's on the same page. Is anybody in disagreement that this is red? We're defining this as red. Good? Okay. So what color is the pen?
Red.
It's red. Okay, put it in the box. It's in the box. Okay. Hang on. Okay. Now, what color is the pen?
Blue.
Is it blue? Wow, that would be something if it was blue. But we don't really know because it's in the box. So we got to guess. We're saying we got one blue, we got one red. Any alternatives to the color of the pin currently in the box?
Well, it's catching on. The absence of light, is it black?
Whoa. So the peanut gallery says absence of light, is the pin black? How many people think, let's take a poll, take an online poll. How many people think that the pin currently in the box is red? How many people think that it's black? How many people think it's something other than that, say like blue? So let's go, we'll go raising hands, which for you is like, just do a hand,
Thumbs up.
thumbs up, that's good. So, I like that, that's great, we'll just do thumbs up.
Because of the delay, they should just write what color. I think. Let's go with that.
Okay,
Yeah. Let's simplify it.
so now that the delay is caught up, I'm asking you to say what color the pen is in the box. And There'll be a pause on your end because we're waiting for the delay to see what you say.
You know, Anthony, I wish there was a way we could look inside the box.
Well, we're going to have to because they're not going to believe. I don't think they're all going to agree.
Well, so far someone says that they like the black theory.
Ooh, that's 2 black theories. 2 blacks, 1 blue. Any other colors that we think it might be?
I'll say red.
Okay, we got 1 red.
It's the same pen that you put
It
in
was
there.
red when I took it out of the box. What do we got?
What about a mix between cyan and magenta? Because that's technically what it is.
Yeah,
Yellow and magenta, sorry.
you are correct, kind of. So I think for right now, just kind of cover this up and think kindergarten. We're going to go back to kindergarten terminology because we're familiar with red, yellow, and blue. Okay, so we're gonna actually look in the box and see what's there. But first, I'd like to do a similar exercise where we don't have to actually go in the box. Now, for the purposes of this, we have to accept that this is also red. This is the same color as the pen. So I'm defining this as red. So we have to accept that premise. It's red. Oh, man. Okay, now what color is it? You're trying to see what the camera says? Well, let me just ask you theoretically, because I know I can see a red tint. So let me just rather ask another question, a different question. Is this the same color now, or is it a different color now?
It's different.
Okay, we got 1 different. Please weigh in. With the lights off, is this the same color?
Can I ask a clarification?
Yes, please.
Is it a property, like when you turn the lights off, the folder itself is still red, it's not like
This is
physically changing color?
this is the
it's not
question I'm
changing.
asking.
Okay.
Is it still red?
To our eyes? No, I don't think so. But the folder itself is.
Okay, well then we got to ask another question. If a folder is in the woods with no one around, is it red?
Not necessarily.
It's a very philosophical question.
Does
now.
somebody need to see the red in
Yes.
order for it to be red?
Yes.
We got 1 yes. Is there a way that we can measure the color with a device besides our eyes?
Hex code.
Brandon is correct that this is a philosophical question. And the reason that we're doing this is because we need to get past this philosophical question. We need to accept that color is something that's measured, that's something that you can measure, and that your eyes are actually a pretty good way to measure color. And the problem is that we could do the same experiment with you turning off your camera or closing your eyes. If you close your eyes, is this still red? Let's try an experiment. We're defining this as red. I'm now going to close my eyes, and we'll see if the color changes for you guys. Yes? Is it still red? Okay, so my eyes being open or closed are an independent variable that have no bearing on the color of the envelope. So that also means that if this folder was here and I left it here and I walked out of the room, it would still be red for you. So it really doesn't matter if somebody observes the folder or not, it's still red. Can we accept that? So your presence or your observation of it do not affect the color. But perhaps the lights do. That's a different color. If you were to measure this color with your eyes, it's going to be different. We don't know what to call it yet. We could call it a dark red because it's not pitch black. But for the purposes of this, the pen is in a box that's pitch black. And nobody is in the box to see it. Is it still red?
Yes.
Okay, we've got a yes.
We had a sure in the chat room.
We got a sure, like maybe. Okay, I think the only way we can do this is to check it out. Do we have what it means to do this?
We have a means to do this. We have another camera. Hi, everybody. We're going to take this camera. It's going to get shaky here in a minute. It's in portrait mode, so if you want to hold that. Oh, you want me to do the holding? Okay, all right.
Well, I don't know.
So we're putting the red folder.
Well, can we set it in there?
Yeah, we can set it in here.
So it can.
I mean, do we want to point it out so people can
No,
see
you-
us? Oh, you want to see the red
No,
pen?
I'm thinking like it lays here and it looks this way.
Do we want to see the pen?
I don't know. Can we see it?
You gotta like put the camera upside down or up sideways where it's.
Can you see red right now?
Yeah, yep,
Okay.
red pen, red folder.
Sweet. Okay, so we're going to actually test this. We all see red.
Oh,
Doing it. I'm trying to do it without messing this up. Okay, we've now eliminated the light from the box. What color is it?
it's waiting.
There's a delay for us. Sorry. You guys probably see it.
You can't see it, so.
You can't see it, but you see something. What do you see?
Black.
You see black.
There's the real-time view into there.
You see black. So, I'm going to ask you this so that we're all on the same page. When the pen and the envelope are in the box and there's no light, I am hypothesizing that that is now black. Is there anyone who disagrees? We've looked at two different variables. We've looked at your presence or your ability to see something. That's one variable. And we've established that that's independent. Because I closed my eyes and it was still red, I left the room and it was still red. So my presence or my ability to see it with my eyes directly is independent of the color. We've also seen that the color changes when the light setting changes, which is another variable, is how much light is in the room. And in this case, we're kind of dealing with both of these variables, but we've eliminated one of them by putting the camera in there. So our presence is no longer a variable, even though we've established that that's an independent variable. The variable about light, however, there is no light outside of the screen light from the camera, and we should be seeing black. We all on the same page. Any disagreements? And let's go with strong disagreements. I have a strong disagreement that that's black. Oh, thanks.
Yeah, I'm back.
Thank you for handing me the red pen. Okay, so basically what we're trying to say is that light is a very important factor in not only your perception of the color, but the color itself and how we measure the color. Light is a factor. So when we're talking about mixing paints, if you draw a painting as in kindergarten or right now, if you draw a painting and you take it into a dimly lit room, the painting itself changes how people perceive the colors and what it looks like. If you go into an art gallery, it's generally well lit for that very reason, so that you can enjoy all of the colors to their fullest extent, and in order to do that, it needs to be well lit. Any disagreements?
None in the chat so far.
Okay. So what's happening exactly, if we go back to kindergarten and we call red a primary color, what's happening when the light is increasing or decreasing? What is actually happening to the color? It's getting brighter, it's getting darker, based on the light. So we know that light from the room is reflecting off of this envelope and into your eyes, which in this case is the camera, and then your physical eyes. Light is involved. Without light, you are not perceiving this color because nothing is going into your eyes. So it's reflective. It's reflective color. These are not the only primary colors. These are the ones that you learned since kindergarten. Today we're going to talk about 3 completely different primary colors. And these are the ones that are most important to us. So let's get rid of red, yellow, and blue. And we're going to eliminate the middleman, which is the light reflecting off of a surface, the middleman right here, going into your eyes. We're now going to have light go directly from the source directly to your eyes. It's not reflecting off of anything. Light is directly going into your eyes. So we can choose the color of that light that's going directly into your eyes, and we're going to choose 3 colors that, if mixed, we can get all of the other colors. So we're looking for the primary colors from direct light colors. Ideas.
Someone's asking, won't that make them blind? The eyes are. Or
No. You have light currently going directly from your screen to your face. And if you are not blind before, you are likely not blind now. So we're not talking about anything harmful. We're talking about the light that's coming from your screen. And the light coming from your screen is not reflecting off of any surface. It's going directly from your screen to your eyes. I could do the same thing with a flashlight. Hey Siri, open flashlight.
Sorry, I can't help you with that.
Of course you
Tom.
can't. Of course you can't. Siri is awful. Flashlight. There it is. Okay. So here's red. For the purposes of the rest of this discussion, let's just call this the same red. I know it's a little different, but we're going to call it the same for theory. So this is light coming directly from my phone to the camera, which is your eyes. For you guys, your eyes. It's not reflecting off of a surface. Here's red. Now, if we mix these colors, coming from a source like a screen or a flashlight or your phone screen, if we mix those, what would the primary colors be, and would they be the same as what we see with inks and paints?
RGB, right?
Okay, we got RGB. Isn't it RBG?
So I said,
No, I was thinking Ruth Bader Ginsburg.
oh,
You're right.
oh.
I was mixing them up. I was mixing up RGB and RBG. Ruth Bader. Okay, so we've got red, green, and blue. Now these are the color names that you've been taught since kindergarten, and these are appropriately applied to direct light. Notice that we're not using cyan, yellow, and magenta, and you also notice that yellow is not one of these colors. which means how do we get yellow? I mean, if you imagine, if you just even try to imagine mixing paints, any paints, together and coming up with yellow, it seems near impossible, because it is. But what if we mix lights? What if we mix different lights? Let's see if I can get it. You got a flashlight, Ad?
All my devices are.
That's all right, that's all right. We'll do it theoretically. Can I bring something on a screen? Can I bring Photoshop up?
Add a flashlight.
This,
It's ready for it. Yep.
is to do colors?
Uh,
Okay,
Photoshop.
Photoshop.
Just prepared for that.
Awesome. Of course. Oh, you even had it up. Is this currently online?
Yep.
Okay.
You want to do the video view up here. Go back for our friends in the audience.
Oh, I see. So they're seeing this.
Yeah.
Sweet. Okay, this works great. I'm gonna actually turn out the lights in the room now. There we go. Okay. So what I'm doing in Photoshop is something that if you've used Photoshop, you've done it a million times. I'm gonna click on the foreground color and get the Photoshop color picker to pop up. And we have here a whole bunch of sets of letters, and we see here C, Y, M, and K, and we see here R, G, and B. We're just going to play with this for right now. The range on Photoshop for these values is 0 to 255. That's a total of 256 possible colors for the red channel. Now, if I maximize that and I say 255, let's see if I have zoom set up. I don't have zoom set up. Oh yeah, I do. Sweet. Then we can see this red. The lights are off in the room, so this is not counting on the lights in the room reflecting off of the red. It's actually coming from the projector, going directly, I guess it's reflecting off the screen, but then it's going directly into the camera and then into your eyes. And this is red. So what happens when we mix, let's say, red, and I'm going to maximize blue here. We get this purplish color.
The zooming isn't showing up on the stream.
Oh, okay. Okay, that's fine. Good to know. Good to know. Let's mix red with green. See what happens. Whoops. I have to make the values 0, and then I'll make the green value 255. Whoa! That is nuts! If I mix red and green, I get yellow. What? Did anybody know this? These are the primary colors that we're dealing with. They're different from the primary colors that you've learned. Those are going to be irrelevant. Don't tell people that red, yellow, and blue are the primary colors, because they aren't, they never were, and they never will be. But that's what you were taught. So the primary colors are cyan, magenta, and yellow for paints and inks and anything where the light is reflecting off of the surface. And for light that's going directly to your eyes, then the primary colors are red, green, and blue. We'll look at just a couple more combinations here. Let's mix red, or I'm sorry, green and blue at their maximum values. And then we've got this kind of light blue, which is also known as cyan. And when we mix, I'm sorry, the one that we just had. Let's see. Yeah, that was yellow, I'm sorry. We want red and blue. And then we get this purple, which is also known as magenta, which is those are two of the colors that I told you were the primary colors for paints, cyan and magenta, and then the third one was yellow. So when you mix two primary colors in one color space, you get the primary colors of the other color space. And when I say a color space, I'm talking about whether it's from direct light or reflective light. And we generally refer to the color spaces as RGB or CYMK. And the K stands for black. That's where the K comes from. They didn't want to use B because it would have confused people with blue. So when we say CYMK, we're saying cyan, yellow, magenta, and black as a practical defense against the chemicals that we use to make our ink. But in theory, we shouldn't need black. Now the nice thing about our computer screens is that we don't have to worry about any kind of nature or chemical elements. It actually fits with theory. Let's put all of the values at 0, and we see that it is black. We don't have to add a fourth ink cartridge. We just mix those colors. And what this means is each of the 3 channels, there's no color being broadcast. And if there's no color at all, void of color is black. So what is it if they're equal amounts of color and they're maximized? That's how we get white. And white light that you see from the sun is a mixture of all of the primary colors. And that's how we get white. Now, how do you get white with paint? It's the opposite. White with paint is void of all colors. So if you have a white piece of paper and you don't put any paint on it, then you could tell people that you just made a beautiful picture of a polar bear in a snowstorm with marshmallow, bag of marshmallows. Say whatever you want. Does anybody have any questions so far?
Would it be fair to say that instead of painting with paint, you're kind of painting with light?
Yes. Yes. Except I think it's important to note that when you're painting with paint, the paint color is dependent on the light in the room. So light is always a necessary element to perceiving color. You must have light. So let's, how do I?
Yeah, just put it up and then turn on the light and it'll be good.
Okay, sweet. Light is a necessary component of perceiving the color. A real life example, if you're going to hike out into the desert and you go to your stylist and you say, you know, I'm going on a hike out into the desert, it's very hot, the sun is above me, what kind of clothes should I wear? I'd like to stay cool, if you know what I mean. What color? I hear white. Now why would that be? Why would white benefit me?
Well, darker colors tend to attract the heat.
Yes. but what they're actually attracting is the light energy. If I'm wearing all black, then my clothes are absorbing all of the light and the light energy, and along with that comes heat. If my clothes are white, then my clothes are reflecting the light from the sun off of me. Anybody who sees me is going to perceive white. So what's happening with the envelope, which, there it is. What's happening with the envelope, if we go back to this being, if we use our kindergarten terminology and call this red, how are you perceiving this as red? What's happening? The light, white light in the room, or from the sun, which is a mixture of all the primary colors, is bouncing off of this envelope, reflecting back into your eyes, except what's reflecting back to your eyes is red. Everything else is being absorbed. That's why you perceive it as red. It is absorbing light. It's only reflecting some light back. And we perceive that as the envelope itself being that color, when in fact the envelope is not the color. The envelope is simply reflecting a light source and only giving you particular colors back, and everything else is being absorbed. Any questions so far?
Couldn't you say that they were all primary colors, just depending on how you use them?
Red, green, and blue are primary colors, and cyan, yellow, and magenta are primary colors, but they're different color spaces, is how we're saying. They are both sets of primary colors in two different color spaces. One is reflected light, and the other is direct light.
So wouldn't yellow still be a primary color?
Yellow is,
I know on a computer in certain spaces you can create yellow, but like, for example, in elementary school, you're mixing markers or crayons and things like that, you still can't make yellow, so wouldn't it be?
yellow is a primary color. That's what the Y is.
Oh, I'm sorry, I'm mistaken.
It's a primary color if, in this color space, in the CYMK color space. No, it's good, we gotta clarify this. This is new stuff. You guys have been taught this your whole life, just not quite accurate.
There's a question in the chat room.
Yes.
Someone is asking, which one is direct?
Direct is coming from your screen. Reflective is the envelope, because the envelope is dependent on the external light reflecting off of it. That's reflective. If I hold up my phone, then this is direct, because it's not reflecting off the surface. The light is coming directly from my phone to your eyes.
You're looking at the light source.
Yes,
right?
you're looking at the light source. So if we're taught, just like Brandon had said, is it accurate to say we're painting with light? Yes. But it's also accurate to say that this too is kind of painting with light, because if this was a red painting, because of the way that this absorbs certain colors and reflects other colors. So for the purposes of this class, for the purposes of everything that you do with the computer, from this point forward, then the primary colors that you're dealing with are direct light, direct red, green, and blue. Those are the three colors that we get all of the other colors from. And when we mix them equally at their maximum, we get white. And when we are equally void of colors, we get black. And if we mix them equally in the middle, then you will get some tone of gray. So if you have equal values on each of the three and they're not maximized, you'll get some value of gray. Okay? And looking at the clock. Okay, I've written 10 digits up on the board, 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the next number in that series? 10, we got 10. How do I write that?
1,
1, 0. Okay, and what we learned back in little past kindergarten, but still elementary school, is that this is the ones place, this is the tens place. What we're actually doing is 10 to the 0 power, 10 to the 1 power, 10 to the 2 power. Let's use 3 digits. We'll use 210. What's happening here is that this is what's known as base 10. This is our counting system. This is what we use every day. We're taking 10 to the 0 power. Anything to the 0 power is 1. And you just have to trust me on that. If you'd like to know why, there's several math classes that'll go on to that here a bit. But for now, just accept that anything to the 0 power is 1. So we're going to multiply this digit by 1, and we get 0. The tens place is really 10 to the power of 1. Anything to the first power is itself. 1 times 10 is 10. And anything to the second power is the base times itself. So 10 times 10 is 100. We also know that as the hundreds place. 2 times 100 is 200. We add those up together, and we get 210. And you guys are not impressed with that because that's what we started with, so it really doesn't say anything. But when we start moving into other bases, you'll see why that's significant. If anybody disagrees with any of this, make sure that you say it. We're going to switch to a different base. We're going to use base 8. Just arbitrarily picking that. Let's look at the numbers in base 8. 0, 1, 2, 3, 4, 5, 6, 7. What's the next number? Remember how we wrote the next number after 9 here? We said it was 10 and we wrote it 1, 0. This is the same thing. In base 10, there is no digit 10. You have to use 2 digits to depict the number 10 in base 10. Same with base 8. If we want to, let's not think of it as 8. Let's think of it as this many. If
Can
we
you
want,
hold that over to that camera now? Sorry.
boom, boom, boom. Which
No,
one?
you're good standing there, just point your fingers at that camera. Thank you.
Thinking 8.
That many.
That many. If we write that in base 8, we write it 1, 0. This is not 10. We call this 1, 0 in base 8. And to designate the difference between 10 and 1, 0 in base 8, we put a little 8 as a subscript at the end of the number, and that tells us what base it is. So let's take a number in base 8 and figure out what that translates to base 10. I'm just going to randomly pick something here. 316. Okay? So we go 8 to the 0 power, 8 to the first power, 8 to the second power. Anything to the 0 power is 1. 1 times 6 is 6. Anything to the first power is itself. 8 times 1 is 8. Anything to the second power is the base times itself. 8 times 8 is 64. 64 times 3 is 192. If I'm wrong about any of this, tell me. But then I'm going to add them up together. 10, 16, carry the 1, 10, 206 in base 10. So 3, 1, 6 in base 8 is the same as 206 in base 10. And that's how we did the conversion. I'm going to show you one more base. Going to do base 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Now if I write down the digits in base 2, we've got a 0 and a 1. And then a 1, 0. So this is nothing. This is this many. But if we want to show this many, we have to write 1 0. So I'm going to come up with a random base 2 number here. Let's do 1 0 1 1.
Can you write that slightly
Bigger?
away from you? Yeah, bigger and over away from those numbers.
I'll do this.
Thank you.
Okay. 1 0 1 1. 2 to the 0. Anything to the 0 power is 1. 1 times 1 is 1. Anything to the first power is itself. 2 times 1, 2. Anything squared is itself, the base times the base. So that's 4. 0 times 4 is 0. And anything to the third power is the base times the base times the base. 2 times 2 is 4, times 2 is 8. 8 times 1 is 8. We add those together, and we get 11 in base 10. So 11, which is this many plus this many, we can write that as 1 0 1 1, and we indicate that it's base 2 by putting a really crappy subscript 2 next to it. This is the equivalent of the number 11 in base 10. So you've now seen you've seen three different bases. We've got base 10, we saw base 8, and we see base 2. And we have different ways of writing the same number. So my question to you is, why, when you have all these choices, did we choose base 10? Why? Why? Why don't we use base 8? It's got less digits. You see 8s in nature more than 10. Theories?
The chat room is alive with theories, actually.
I'd like to hear them.
Someone is saying that base 8 is just like base 10 if you're missing 2 fingers.
Interesting.
And then another person replied already to say that this is because of our fingers.
Well, I believe you are correct. This is why we use base 10. If we were the Simpsons, we would use base 8. It's the only reason. There's nothing in nature other than our fingers and our toes that really point us to using base 10. So all this stuff you learned about the decimal system and how easy it is, it's easy because we can count on our fingers when we're young. That's why we use it. There's otherwise no reason to use base 10. You could use any base you want.
And this question came up last semester. I think someone asked us if any cultures use something other than base 10, and didn't we find?
Yeah, Brandon found some cultures that did use different bases.
And one of them was surprised. It was base 12 that another culture used.
Yeah.
That took me by surprise.
Well, it doesn't surprise me because where do we find 12 in nature? Yeah, but why is it a dozen? What's special about 12? What's special about a dozen? It's how many months there are. It's how many times the moon goes from waxing to waning.
Someone said donuts too.
13 actually.
Baker's ovens.
I'm thinking if cops made the numbering system, we wouldn't be using any of these. So we're gonna discredit the donut theory. So base 2 does happen in nature all the time. And if you look at what the components are of base 2, it's 0 and 1, which is the same as these, on and off, on and off. 0 and 1, true and false. This is the numbering system that the computer uses. The computer loves base 2, zeros and ones. That's how your computer understands everything. So when we're connecting with the computer, we need to translate everything we do to base 2 so that the computer can understand it. And earlier computers were based off of switches. And people that make circuits are used to using on and off, but you'll see that in early computing that these on-off switches were used since the beginning of computing. So what that is called is binary, and a 0 and a 1, those are binary digits, 0 and 1, and we call that a bit. Binary digit, bit, binary digit. If we put 8 bits together, we call that a byte. A byte is 8 bits. And then from there you can get all of those other numbers that you're used to hearing. Megabits, gigabits, megabytes, terabytes. It's all based off of binary and larger numbers of binary digits. So what we need to do is figure out a way so that the computer can get this byte, but there's no way that we're going to talk to each other this way. Well, what's the number that you want me to put in? I want you to put in 011001110. Who's going to talk like that? Human beings cannot handle this. So we need a shorthand. We need a way to do this very thing. Now, if we look at all the possible combinations of a byte, 2, 3, 4, 8 digits. We've got 2 possible combinations here, 2 here, 2 here, 2 here. It's 8. It's basically 2 to the eighth power. Somebody's got to figure that. 2, 4, 8, 16, 32, 64, 128, 256. There's 256 possible combinations of these 8 binary digits. Does this number look familiar to anybody?
Isn't that the possibility of colors?
It's what we were doing in Photoshop.
Yeah, it's how many possibilities you can have of one
Yeah.
color.
Yeah, so really what we're saying is that each channel, the red, the green, and the blue channel, can have 256 possible values. And then we can tell the computer those values using a byte, which is 8 bits in binary. Now this is easy for us, 256, but there's just one more base I want to show you. It's base 16. 5, 6, 7, 8, 9. Oh. Now I got to put down 15 different digits in there, because remember base 10 has 10 digits, base 2 has 2 digits, so base 16 probably has 16 digits, but we don't have anything past 9. I can't put 10 because we already know that that's going to be 16. So what do? We're out of numbers. Well, fortunately, we're going to borrow from the alphabet. So we've got A, B, C, D, E, and F. And if you look at the A is equivalent to 10 in base 10. B is equivalent to 11. C is equivalent to 12, 13, 14, and F is 15. Okay, and if we were going to say write something in base 16, let's do something that's not going to kill my brain. Let's do 2E in base 16. So we're going to translate this 2E in base 16 to base 10 so we know what this is. So we say 16 to the 0 power, 16 to the first power. Anything to the 0 power is 1. We know that E is the same as 14. So that's 1 times 14 is 14. Anything to the first power is itself. 16 times 2 is 32. And if we add those up together, we get 46 in base 10 is equivalent to 2e in base 16. And notice how we say that. We say 2e. We don't, if it was a 0, we don't say 20 in base 16. We say 20. Because 20 is a value that only happens in base 10. We don't use that in any other bases. So when we're talking about the digits, when we're talking to each other verbally, we would say this is 20 in base 16. Okay. So how many possible combinations with 2 digits can we get? We've got 16 combinations here. We've got 16 combinations here. What's 16 times 16? Say it! Oh, you don't know already? You guys aren't jumping ahead? I'm just going to jump ahead.
256.
256! 256! 256 on Photoshop. They're all the same. So what we can do, instead of having to memorize 8 binary digits for each value, or having to do this crazy conversion thing that you just saw me do with 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, then what we do is we use base 16. Because we only need 2 digits to make a byte. This is equivalent to 8 binary digits, which is a byte. So if we want to write a byte, a value, we can do the shorthand using base 16. And the way that we tell everybody that it's base 16, I'm just going to write a number up here, 23E601. The way that we tell the world that this is base 16 is by putting a subscript 16 to the right. That's one way. Another way is to go 0x. You won't see this as much, but it's a common way to show that it's base 16. And probably the most common way to designate this as base 16 is to use that symbol, which is called, correct, thank you, it is called the pound sign. Oh, I'm sorry, this one.
Oh, yeah, wait.
What do you mean? It's a hashtag.
It's not a hashtag. Nobody hashtags hex values. Do they? It's not a hashtag. So let's just make this very clear. Hashtag, not a hashtag.
Call it hashtag.
Boom. So that brings us over here. You'll notice that I have 6 pairs of values. If we divide these, if we divide those into chunks of 2, and remember, 2 hex, and I say hex, base 16 is called hexadecimal, but we often say hex. So if we divide it into 2 hex digits, like this, then this is a total of 24 bits, 24 binary digits. But it's also 3 sets of 8, which is 3 bytes. So this is 3 bytes of information. And the way that this works is that the first pair is red, second pair is green, and the third pair is blue. Always in that order. It never changes. This is what we've agreed to do. So the first pair is red, second pair green, third pair blue. So don't think of Ruth Bader Ginsburg when you're doing this. Think of red, green, blue, RGB, RGB, RGB. Because that's how you're going to translate these things. So when I write pound sign, FFFFFF, that's the maximum value in each of the 3 channels, R, G, and B. What color is that going to be?
What?
We got whites. Any disagreements?
I think the chat room agrees.
And if we want to show black, we have 3 pairs of zeros, which is no color value for each of the 3 channels. And if we wanted to show a maximum, let's say blue, this is red, green, blue.
And someone in the chat room beat you to that.
Oh.
They already wrote pure blue.
Oh, sweet.
Can I tell you what they think pure green is?
Yeah.
00FF00.
Sounds good. And then we got red.
No, there was a question in the chat room. I hope I can ask it right now. How come the maximum values are 255 in Photoshop and not 256? Because you said there were 255.
Because we have to consider that 0 is a value. And we're not dealing with, we're dealing with integers. So there's no 1.5. It's going to be a range from 0 to 255, but only the integers, and that is a total of 256 possible combinations. 0 counts as a combination. So that is why we have this number. That's where it comes from, and you should be able to identify how to write the 3 primary colors that are direct light colors. You should be able to write those in hex. So red, FF0000, green, 00FF00, and blue, 0000FF, and also black and white. And then you should also be able to know how to do gray. And any combination where they're the same, I'm just randomly picking something up, A2, 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 that's a shade of gray because they're all equal. So you can kind of get an idea of what color things are just by looking at the values and seeing, are they closer to 0 or are they closer to 255? So if we just, let's have somebody do a random one. Just give me a random 6. Random 6. Don't care what they are. You guys can too. Yell some numbers out. Throw in some letters.
A4.
A4.
Go ahead.
5.
5, we'll go 05.
D.
7.
F. Oh, yeah.
DF? You sank my battleship. Okay, so let's figure out what color this is. We've got RGB, and we look at the red. A is 10, so it's kind of in the middle between 0 and 16, but it's closer to the 16. So this is going to be a closer to a maximum value, but it's somewhere in the middle. Green, 0.5, that's really low between 0 and 255. So this is hardly any green value. And then DF, we know that D is 13 and F is 15. So this is actually pretty high value. So this is going to be very bright for the blue channel. So we've got a mixture of red and blue, and there's no green at all. I mean, there's a little bit, but hardly any. And we gotta guess what color that is, and it's mostly on the blue side. So what did we say when we mixed red and blue? Does anybody remember what we got? Because you would have to remember, because it's hard to figure out because you're not used to this color space. You've always been working in the other color space. Now you're in this color space. You have to get used to what this is going to be. So RG, or the red and the blue mixed together, what do we get?
I know.
Wasn't it a
I was
magenta?
going to say
It's
that.
like a purple.
Yeah, well, let's actually,
It's this color. Like this here.
I just gotta do.
Oh, I gotta get you logged in, sorry.
Oh, I'm sorry.
I didn't realize it was
I
locked.
started putting stuff in.
The password is not this purple color.
Yeah, I think I put magenta in.
There you go. Can you hit the video mute button on the screen? So
Yeah.
I can see it
Okay. I covered up what the number was. A405DF. 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 And you'll notice that I typed that in this field that we didn't look at before, that's right next to the pound sign here. And as soon as I did that, then the red channel and the blue channel were right there. Just like we typed, it translates that to base 10. But this is, we look at it and it's a dark magenta. So that's how all this stuff relates together. Does anybody have any questions? So we went from primary colors, looked at binary digits and other bases, and then how we're using base 16, hexadecimal, also known as hex, to write colors. The first pair is red, second pair is green, third pair blue, and that's all I got.
I have a question for you.
Yeah.
Hopefully you can keep it short. How many possible colors are there?
Well, if we take 256 values for each channel, 256 times 256 times 256, we get what is known as millions of colors. And I'd have to do the computation to give you the exact number, but it's 16 million colors. Okay, so are there 16 million colors in nature? No, there's way more. It is an infinite number of colors in nature. Our eyes do not perceive the difference between colors at that kind of rate. So this is good enough for us. However, there are ways to be more accurate with color that are beyond this system, and Brandon theorizes at some point that this is going to be more mainstream. But at this point, for most of what you're doing with web design and even in art and graphic design, then millions of colors is adequate. I think as technology increases and the screens are able to depict more accurately those fine colors more than a millions, then we're going to see a different way of depicting those values. But for now, this is pretty mainstream, and you're safe to use this for most everything you do.
Okay.
Someone had a question.
Yeah.
Lisa.
Someone wrote in the chat room that they have questions about assignments. I will ask that you send those questions into the Slack chat room instead of being answered during this part of the lecture. I do want to cover one more topic, and it's just to tie together what we've been doing in Photoshop with what you're doing in Atom. So I think I have Atom installed on this computer. Let me get it opened up here. Yeah, just a second. So while that's opening, you have been probably just blindly typing in some of those hex values for now. Anthony showed you how to use Photoshop to type in the hex colors to see what actual color shows up. Someone in the audience here just type that hex number right into Google, and Google will show you any value, any color value based on what you type in. The web inspector, which we spent all of last week talking about, has a great color picker. If you actually open up the web inspector and you click on the color, you should be able to get an interface similar to what you saw in Photoshop that lets you mix the colors, drag it around, find the hex code for it so that you can type it into your CSS. Or CSS offers a couple more powerful ways to write colors, and I want to just go over those real quick. Anthony, can you go to my computer?
Yeah.
Be careful with the trackpad if you can select VNC over here.
Sure.
That'll show the screen, everyone. So I'm going to put
I'm not seeing it.
VNC on the far left. VNC only, sorry.
Oh, okay, okay.
Sorry about that. I'm going to put Atom in CSS mode. So as you've been writing something, like let's say that I'm making my body have a background color. As I'm writing background color, you've been able to write hex, like FFF, FFF. And with certain plugins in Atom, you can actually have that show you the color as well. What I wanted to show you is that there are a couple other equivalent ways to write the color FFF, and we determined already that that is what color? White. So that was another way that you could make something have a background color of white, is just by typing in the keyword white. There are a couple dozen named color values that you can write in CSS. There's a special shade of purple as well out there that you can write a name for a color. Now you know two ways now, the name of the color and the hex. There's a third way, and it's very similar to Photoshop. It is RGB, right? So RGB, with these parentheses, allows you to specify the color ranges of red, green, blue as integers. Instead of having to write hex, if you have an aversion to hex, you can actually just write those numbers. And the numbers that you write are that 0 to 255. So if I wanted to make this color white, that would be 255, 255, 255, making all of those channels the maximum values to say all the light. I want all the light. So that is the third way to write colors in CSS. And I want to cover a fourth way because it is a very powerful way to mix colors on a web page. And it's very similar. Instead of RGB alone, Atom will show you that there's an RGBA color scheme. This takes the same three values at first, 255 for red, 255 for green, 255 for blue, but it adds a fourth number. And it's not a number that goes up to 255. It's actually a percentage, a decimal that goes from 0 to 1. So now we're mixing these integers with other numbers. But what that allows you to do is either write 0 or 1 or any value in between, like 0.5. And what this color represents at the very end, that is the alpha channel. That's how transparent it is. So if you find yourself wanting to set a color and allow a background image to come through, or if you wanted to layer two different objects on top of each other in CSS on your web page, you could allow an alpha channel, which allows the stuff underneath to bleed through. And now you're really painting with light. You're really mixing the colors. So you can write colors 3 different ways, and that was our goal with this lecture, is to introduce the new primary colors that you'll be using, understand how the computer understands those, understand that you don't have to write 16 million color combinations, you can use hex as a shortcut, and finally show you how to write that in ways that are easier in Photoshop, the Web Inspector, and Atom. So thank you for joining the stream. We will see you next time.